Hi, this is Tyler Zavalis in Mr. Roberson's AP Physics C class. Today I'll be reviewing key concepts of physical systems and principles as related to roller coasters. To begin, let's talk about energy. What is mechanical energy? Although you may have heard of the word energy in physics is a scalar quantity that is measured based off an object's motion, state, or condition. There are two types of this mechanical energy. There's a kinetic type of energy and a gravitational potential type of energy. Kinetic energy is determined based off an object's motion, speed, or velocity, which are all kind of used interchangeably, although they have slight differences in meaning. The equation for this is 1/2 times the mass times velocity squared, where the energy is in joules, the mass is in kilograms, and the velocity is in meters per second. Gravitational potential energy, on the other hand, has to deal with the height of an object above the Earth's surface. It's the separation of these two objects, the Earth and the smaller object, that creates energy. The equation for this is the mass times the gravitational constant times the height, where once again the energy is in joules, the mass is in kilograms, and the height is in meters, and then g is going to be the gravitational constant. So just a reminder, kinetic has to do with motion, speed, while gravitational potential has to do with the height above the Earth's surface. So how do kinetic and gravitational potential energies relate? The two ideas seem pretty separate. There seems to be no link between the two. But in fact, there is. And the answer ultimately is the principle of conservation of mechanical energy. And this principle is pretty important. What it essentially says is that for an isolated system where only conservative forces are acting on it, which means the curl is zero for people in multivariable calculus, that the sum of the mechanical energy in any point is going to be the same, regardless of what point along its motion or path you take. So as you can see here, the mechanical energy initial and the final will be equivalent. And then if you break that down into gravitational and kinetic, you can simplify it, and then you can plug in those equations from the previous slide to get this equation to find conservation of energy at any point. That's all fine and dandy, but at the end of the day, this seems pretty unrealistic. I mean, there's always going to be some external force, right? What if the system's not isolated? What if there's a frictional or drag force acting on it? There's actually an answer for this. Work is a concept of energy being added or transferred from a system based off an external force acting upon the system. As you can see here, work is going to be the change in mechanical energy, or the final minus the initial energy from the system. We also have a line form, or a line integral form of this, which is the force dotted with the radius r coordinate. This can be simplified as a function of the force as a function of r times the cosine. We describe the different types of work. Positive work is representing a transfer of energy to the system that's basically aiding the motion, while negative work, on the other hand, is representing a transfer of energy that is from the system, which is impeding the motion. And frictional and drag forces are common examples of negative work in systems. So consider a ball. While a ball is moving up, there's going to be negative work on it by the gravitational force. While it's moving downward, there's going to be positive work on it as it speeds up. That seems pretty straightforward. So let's consider the negative work, the frictional and drag forces that I was just talking about. An example of losing energy is known as thermal energy.
This is kind of an eternal energy that is lost as a result of frictional forces on an object. Thermal energy can usually be characterized as the loss of energy of mechanical energy. It's just a type of work, essentially, found in the system.
Alright, so let's begin with the roller coaster. So as we leave the lift station, there is zero gravitational potential energy. We have kinetic energy from the lift, but it's pretty small. As we go up the lift hill, the gravitational energy is being increased. As you can see here, we've had an increased gravitational potential energy as we've gone up, and the height has increased. This is a force of work done by the lift chain on the train to increase the energy of the system. As we crest the hill here, we're going to have a maximum of gravitational potential energy and a momentary stop of kinetic energy. As we go down the hill here, we're going to see a quick transfer of gravitational energy into kinetic, as well as thermal. As you can see here, there's zero gravitational once we hit the floor. Okay, on to the next topic. G-force. G-force is known as the magnitude of the gravitational force that your body feels on any point on a roller coaster. It's not actually the gravitational force, it's just the measure of weight that your body feels at a certain point. So as you hit this trough underneath a hill, your body's going to feel pushed down more, so you're going to have a positive G-force. Well, if you're on a hill, your body's going to feel a little bit weightless, and you're going to have a negative G-force. And this is because of Newton's first law. Your body's going to want to keep moving in the direction it's already moving. So your body's going to want to either stay down or stay up. Alright, there's more than just positive and negative. So let's do a quick comparison of the 4 different types of G-force. There's positive and negative, as well as linear and lateral G-forces. And there's different amounts that the human body can handle, so I'll make sure to include that as well. So positive, as I said before, is when the human body's going to want to keep continuing downward, but the track's going to move upward. And there can be up to 5 Gs, but your body is going to feel heavier, as you can see here. Let's look at this. So as these people fall down the hill, in this trough, their body is going to feel a lot heavier because the track is moving up, but their body is going to want to continue going down. Negative is a little bit more dangerous. It needs to be less than 2 Gs, and this is what airtime is. And a lot of roller coasters utilize airtime. So as you can see here, these people are going to feel a sense of weightlessness, not completely, but it's the airtime that you get flung out of your seat for, and you can literally see these people out of their seats on this. Linear, as implied, is the linear system, usually used for launch systems. You can handle exorbitant amounts of 17 Gs. It's mainly used for launches when you're moving, accelerating in one direction. There are people going to feel pushed into the seat back, essentially. And then lateral, as implied, is going to be from side to side, and it's going to feel like you're flung out to the side of the car. And there's no limit particularly, but this needs to be properly restrained in order to be safe. So yeah, wild mouse coasters like this, you're going to feel flung to the side of your car.
Let's get into a specific element of roller coasters: linear inductive motors. Launch systems are used in a number of roller coasters, and the LIM was the first to effectively do so. These systems use electromagnetic elements, as well as current, to propel a roller coaster forward at fast speeds. So in this diagram, there's things called stators, where there's 2 blocks, and they're usually in pairs of 4 that move down the track, while there's fins on the underside of the roller coaster frame that pass through the 2 stators. And essentially, there's going to be more force with each one. Flight of Fairking's Island was the first use of these systems. Let's watch the roller coaster launch first, and then I'll explain what's occurring. Alright, so along the launch track there are a series of powerful electromagnets embedded in the track in structures called stators. These are full of magnetic wiring energized with alternating current. The underside of the roller coaster train is fitted with conductive metal fins, as I said, with some aluminum or some metal. When alternating current is applied to the electromagnets on the track, It creates a constantly shifting electromagnetic field that continues down the track. As the metal fins on the train pass through this moving magnetic field, an electric current is induced within the fins. This is because of Lenz's law, where a changing magnetic field through a conductor induces an electric current within that conductor. These induced currents in the fins, in turn, create their own magnetic field, and this induced magnetic field opposes the original magnetic field from the track. The interaction between the opposing magnetic field of the train's fins and the moving magnetic field of the track creates a repulsive force. This force, as a result, pushes the train forward, propelling it along at high speeds.
But now let's put this into practice. So I'm going to use real values from Orion, the roller coaster at Kings Island, and we're going to calculate values and compare them to what the actual values are. So the station begins at 4 meters tall above ground. The lift hill goes up to 91 meters. There's a degree of declination of 85 degrees. And then we're going to have 3 different states for the train on this roller coaster. So the mass is going to be 2,240 kilograms. We're going to assume that for a normal train car. And then our first question is, what is the magnitude of work done as the train moves from point 1, the station, to the crest of the lift hill, point 2? Okay, to begin, let's use the energy work theorem, which energy 1 plus the work done on the system will equal the energy at point 2. Basically, let's break this energy 1 down into the gravitational and kinetic as well as point 2. Since we're going to assume that there's no velocity at point 1 and point 2, we're going to simplify those, and then the work is going to end up being the difference in gravitational energies between the 2 points. Let's plug in those equations that we used earlier, and let's factor out the mg to find work. Let's plug in our values that we have, g being 9.81. And we're going to find that the work done on the train is 1.9 times 10 to the 6th joules. That's a pretty high value. So essentially what happened is that work done 1.9 times 10 to the 6th is how much work that the chain induced onto the system of the train and Earth while it traveled up the hill. All right, on to our next part. We're going to assume a coefficient of kinetic friction of 0.3. And we're going to ask, what is the final velocity of the train once it has reached the bottom, which is essentially 0.3. So to begin, let's draw a force body diagram at any point on the decline, because this is where we're going to use kinematics and forces to simplify our problem a little bit. Obviously, it's not going to be 85 degrees perfect over this point, but we're just going to assume. So first of all, we have the force of gravity, and then let's break that into its components just to find the normal forces. So using trigonometry, we can simplify this into its components. And then the normal force is going to be the opposite of whatever that y, if you want to call it y coordinate. And then the kinetic friction, the frictional force will just be the normal force multiplied by the kinetic friction coefficient. So there's our free body diagram. On our, if you want to call it x-axis, we have the component x of the force of gravity subtracted by the kinetic friction force. And this is going to be the only forces acting on the train, parallel to the track, which is what we're focused on, because the y coordinates will balance out. So if we plug in for this, and we know that F equals ma due to Newton's second law, acceleration, once factored out, is going to be the gravity coefficient g times sine 85 degrees minus the kinetic coefficient friction times cosine 85 degrees. Now let's find how far that the train traveled on this point using trigonometry. So we have 91 as the height. We're looking for the length, the hypotenuse, and then we know that angle is 85 degrees. So using some trigonometry, we can solve for the length that the roller coaster moved on this part. As you can see, the triangle is not a perfect approximation, but we're going to use it because it is the closest way we can using kinematics equations. Now let's use the kinematics equation. The velocity squared is equal to the initial velocity squared times plus 2 times the acceleration times the change in the coordinate that we're using. And the coordinate's not the x, but it's the segment that you can see from x to x0. And if we solve for this equation, velocity is going to equal the square root of 2 times the acceleration times the length. And if we plug in our values for that, we can solve for the velocity of the train once it reaches the bottom of the hill, which is 41.7 meters per second or 93.2 miles per hour. In actuality, the roller coaster moves at approximately 91 miles per hour, at least according to Kings Island. So obviously there must be some forces. We did use approximations, this is not surprising. But the fact that it's that close is very inspiring. Alright, and on to our last question. How much energy was turned into thermal energy, converted into thermal energy as it moved from point 2 to point 3? So this is going to be the energy that was lost of the train over this point. So to begin, let's use the same thing that we used for part A. We're going to use the work energy theorem. Like I said, thermal energy is just a type of work. So the energy at point 2 plus the thermal energy is going to be the energy at point 3. So at point 2 there's only gravitational energy, and at point 3 there's only kinetic energy. So then we can solve for thermal energy and plug in the equations that we've been using. We know thermal energy is going to be negative work because the train is slowing down and it's losing energy. Energy is being taken from the system. So we're looking for a negative answer. So let's plug in our values using the velocity from the last question. And we find that the thermal energy transferred from the system is negative 5.2 times 10 to the 4th joules. And like I said before, notice it's going to be negative work.